order differential equation, when we talk of exact equation, it is typical in first order differential equation. Usually it is homogeneous in expression. For example, if you are given 3x into xy minus 2 differential x plus s cubed plus 2y dy equal to 0. This is said to be an exact expression, and we are supposed to solve it as an exact first order differential equation homogeneous. So we open the bracket to be 3x squared y minus 6x differential x plus s cubed plus 2y differential y equal to 0. Based on the rules of exact equation, in exact equation, partial n function of x comma y partial y is usually equal to partial n function of x comma y partial x. Once they are equal, it is said to be an exact equation. So we have to test for exactness first before solving the exact problem. Now, partial derivative of n is partial 3x squared y minus 6x respect partial y. If we differentiate this partially, this implies that the derivative of 3x squared y is going to give us 3x squared, because we are only differentiating y derivative with respect to y, and that is 1. To multiply 3x squared will give you 3x squared. So we'll be having 3x squared here. Now minus 6x, if partialized with respect to y, gives us 0. Furthermore, partial n is this function. Take note that this is n function of s comma y. This is n function of s comma y. These are the attached derivatives to the two sides of the questions. So this gives you partial n x comma y is partial derivative of s cubed plus 2y to respect x. And if you partialize this with respect to x, we are going to get 3x squared. So you can see how the partialization of this with respect to y and partialization of this with respect to x are equal, 3x squared and 3x squared. So this is an exact first order equation. Once it is exact, we now see function of x comma y is equal to the integral of the first expression, which is 3x squared y minus 6x differential x plus arbitrary constant function of y. Now, if it is integral of 3x squared y minus 6x differential x plus k is a function of y, you discover that when integrated, this will give us 3s cubed over 3 multiplied by y minus 6x squared over 2 plus arbitrary constant k is a function of y. When this is integrated, take note, this will now give us s cubed y minus 3x squared plus k is a function of y. Take note. K is a function of y, and that is function of s comma y is equal to this. Now, when we have gotten this expression, it is taken as first equation of first instance. We will now have to partialize it. Partial f function of s comma y, partialize it with respect to y, and this gives us s cubed by differentiating by 1. And also, we are going to partialize with respect to y. This will give us 0. Now plus dk dy. Take note, which is also k prime. At this juncture, we have to compare this equation with the other part of the expression that we have not touched, and that is this part of the expression. So that this is equation 2. When this comparison, this juxtapose is done with this expression, which the subsequent partialization after integration of this gave this, we now compare. When we compare, we'll be having x raised to power 3 plus dk dy is equal to what you have here. And what you have here is s cubed plus 2y. So that this is a replica. They are of same function. They go away when you subtract both sides. So that we will now be having dk dy is equal to 2y. When dk dy is equal to 2y, because these are subtracted from two sides, remember that this entity was related with the last part of it since we started with it. Then, tradition of exactness is that the decay is equal to 2y multiplied by dy. When the variables are collected, we are taking the variables. So we now integrate decay and integrate 2y dy to finally get constant k, a function of y, is equal to 2y squared over 2 plus c. Now, progressively, this will give us a function of y is equal to y squared plus arbitrary c. We are done because this was the k function of y that we are searching for, the k function of y. Immediately you get it, it will be inserted in equation 1 to get the final answer for the exact equation. So the final answer for the exact equation becomes function of x comma y is equal to s cubed y minus 3s squared plus y squared plus c. This is the answer to the exact first order differential equation. Take note of the procedures. It is fundamental that the first thing is to do the exactness test. 3s squared, 3s squared, they are equal. 3s squared, 3s squared, they are equal. So when 3s squared is equal to 3s squared, because partial m partial y is equal to partial n partial x, based on the exactness test condition, at that level, you can now progress to find the integration of this first part with respect to dx. Whatsoever you get, you will now peg k function of y to enable you to get the right hand side part of it and add to it. So after the subsequent integration and partialization, we have, after the integration we have this, which is equation 1. Then the partialization with respect to y gave s cubed plus dk dy. So we compare this expression with this part of the equation, and you will see a value exactly the same, which is s cubed plus dk dy equal to s cubed plus 2y. You can see. So this goes off the equation because they are two parts. When subtracted, gives 0. So dk dy is equal to 2y. Integrate both sides. That is to say, taking the separation of variable technique into play. Dk dy is equal to 2y. So separation of variable technique, dk is equal to 2y dy. Integral of both sides gives the value for constant k, function of y, which is now y squared plus c. This y squared plus arbitrary constant c will now be inserted into equation 1 to get the exact equation solution, which is function of s comma y, s cubed y minus 3s squared, which is here. Now the k function of y that you have solved for will now be added, which is y squared plus c. That is the entire solution. Take note.